This video is on section 8.2 notes, systems of linear equations in three variables. So the graph of the solution set of a linear equation in three variables requires a three-dimensional coordinate system. And that's because we have not just the x and y axis that go left and right and up and down, but we're also going to have the z axis, which adds depth. So you can see here's our linear equation in x, y, and z, written as ax plus by plus cz equals d. And the solutions are going to be written as ordered triples instead of ordered pairs. So instead of writing xy, where you have two lines that intersect, we're going to talk about 3D shapes that intersect, and it's going to be xyz. So 3 dimensions because we have not just left and right and up and down, but we have left, right, up, down, and then some depth. And so we call these three-dimensional graphs of a linear equation planes, and you can think of a plane as like a sheet of paper, is kind of what a plane looks like. So here's your three equations in your system, and so it's three sheets of paper that are kind of like intersecting, if that makes sense. So here is an example of a coordinate that is graphed in a three-dimensional system. So you can see the z-axis is labeled right here, that's left and right. The y-axis, I said z-axis, I meant x. So the x-axis is left and right like normal. The y-axis is up and down. And then you can see the z-axis is that depth, kind of bringing it forward. So if we were to do x, y, z, the x-axis for this point, you can see it's kind of three-dimensional. The point is to the right 1. If you measure how far up and down the point went up 3, and it's kind of hard to see that 1, 2, 3, but you can imagine it's like coming forward a little bit. And then for the z-axis, they're showing that they've brought it forward 2. So 1, 2, they've brought it forward 2 from the x-axis. So I'm not going to make you guys graph in 3 dimensions because it really messes with my brain, and honestly, unless you do something that's really nuanced, you're probably not going to be graphing in 3 dimensions, but that's how it works. Okay, so we're going to have a single solution for a system of equations in 3 variables if, like I said, we have our 3 planes that are intersecting at a single point. And this is a pretty unique situation, and honestly, even though this is going to be the majority of what we deal with solving for this section, it's probably something that would be pretty rare for 3 sheets to intersect in exactly 1 point. But that's what a single solution would look like. So, and we would say that this is a consistent system if it has a solution. That's what consistent means, it has a solution, and independent if the solution it has is exactly one solution. So first we're going to be looking at independent consistent systems. So this is going to be the most common type of solution that we find today, and here is our process. So first we're going to look at the 3 equations that we have. And we're going to choose 2 of them to eliminate one of the variables. And it doesn't matter which variable you start with, you're going to look at whichever one looks the easiest to eliminate. After that, you're going to choose the 3rd equation that you ignored, and you're going to go back to one of the 2 equations that you started with, and you're going to eliminate the same variable. And at this point, you're going to have a system of equations and 2 variables. 2 equations left, 2 variables. And then we're going to go back to what we learned in section 8.1, and we're going to eliminate another variable. And at that point, you're going to solve for the remaining variable. So you have 1 variable you've solved for. You're going to go back to step 3 where you had 2 equations and 2 variables, and you're going to take the 1 variable you've solved for and plug it in and find the 2nd variable, and then you're going to go back to the original equations and you're going to take the 2 variables you've solved for and plug those in, and then you'll have all 3 variables. And your last step is to write your answer as an ordered triple XYZ. Okay, so we're not going to actually do the problem yet. We're just going to kind of map out the steps for this problem. So when I looked at this problem, really all three of these variables, x, y, and z, are not terrible to start off eliminating. But when I looked at this problem, the first thing I saw was that positive 3z and negative 3z would eliminate easily. So the first thing I wanted to do was look at equation 2 and equation 3. And eliminate z. So that means my next step is to take this first equation that I haven't worked with yet and use this first equation with one of the other two. It doesn't matter which one. So I can see that equation 1 has a negative z, so I'm going to use equation 2 that has positive z's, and then I'll cancel the z's out. And of course I'm going to have to take the first equation and multiply it by 3 to make that happen. So that's going to be my second step when I go through and solve this. Equation 1 and equation 2, and again I'm going to eliminate z. So when I'm done with that step, I'm going to have two equations that are in terms of x and y. That's what I'll have in that step. And we haven't gotten there yet, so we don't know what variable is going to be the easiest to eliminate when we get there, but I'm just going to give you guys a peek into the future. It's going to be y. So at that point, we're going to eliminate y. Once we've eliminated y in the fourth step, we're going to be solving for x. When the y is gone, the x is going to be the only variable left, and so that's what we solve for. And then we start to go backwards. So once we have x, we're going to go back to our two equations that are in terms of x and y. We're going to take the x that we solved for and plug it into one of these two equations. It's not going to matter which one. And then we're going to solve for y. And then we're going to go back to the very beginning, to the original equations, and we're going to take the x and the y that we've already solved for, and we're going to plug them into one of the original equations, and we're going to solve for z. And then our last step, once we've solved for x, y, and z, is we're going to write the ordered triple x, y, z. We're going to write it as an ordered triple. So this is how the steps are going to work on this specific problem, but of course each problem is going to be a little bit different because you can eliminate variables a little bit differently from the beginning. Okay, so let's go ahead and get started with that. So first step. I'm going to work with equation 2 and 3, and I'm going to eliminate z. So I have 3x minus y plus 3z equals negative 2. X plus 2y minus 3z equals negative 1. And when I combine those together, I get 4x plus y, the z's cancel, equals negative 3. All right, now I'm done with equation 2 and 3, so I have to work with equation 1, and I decided to work with equation 1 and 2. And to get the z's to eliminate, I have to take equation 1 and multiply by 3. So I've got 3x plus 3y minus 3z equals 0. In equation 2, I'm just going to copy down exactly as it is. So 6x plus 2y, the z's have eliminated, negative 2. So now I have two equations and two variables, so I'm just going to bring these two together. 6x plus 2y equals negative 2, 4x plus y equals negative 3. And at this point, you could do elimination or substitution, to be honest. That's what we learned in section 8.1. But whenever I'm doing these, I kind of get in a rhythm of doing elimination. And so that's what I'm going to do, is I'm just going to keep up with elimination as my method of solving. So we decided, I decided that we would eliminate the y's, that it would be a little bit easier. So if this is positive 2y, I want this one to be negative 2y. So I'm going to multiply the second equation by negative 2. I'm just going to copy that first equation down. And then the second equation is negative 8x minus 2y equals 6. And so I have negative 2x equals 4. And I'll divide by negative 2, and x equals negative 2. So we eliminated the y's, we solved for x. So now I'm going to go back to one of these two equations, or really one of these two equations, it doesn't matter. And I'm going to use that to solve for the other variable in the two equations and two variables. And the other variable I'm solving for is y. I'm going to choose this second equation because the numbers are a little bit smaller. So 4x plus y equals negative 3, and my x was negative 2. So negative 8 plus y equals negative 3. So y is 5. And then I'm going to take the x and the y that I found, and I'm going to go back to one of the original equations. And I'm going to go back to the first one. So x plus y minus z. X plus y minus z equals 0. 3 minus z equals 0. So 3 is z. And so my solution as an ordered triple is negative 2, 5, 3. And that's it. Okay, so that is one type of problem we're going to look at. This next type is not going to be as common as far as the type of problems that we're going to run into. But honestly, it might be a little more common as far as like naturally speaking what might happen if you had 3 sheets of paper that were to intersect each other. So if the planes are parallel, if the 3 sheets of paper, and when I'm talking about paper, I'm using an analogy here. I'm not literally saying they're pieces of paper. But the XYZ plane or an XYZ graph for a linear equation is going to look like a piece of paper. So if those pieces of paper are parallel, then there's no common point. There's no single point where they intersect and no solution to the system. So that's one possibility. And we'll look at that next. If 3 planes intersect along a line, then there are infinitely many points on the line that satisfy the 3 equations. So this is back, we're thinking back to section 8.1, where we had 2 lines that when we graphed them, they ended up being on top of each other. They ended up being the same line, and we had infinitely many solutions. And if that was the case, we would say, okay, you can find x, y, but you have to plug points into this formula. You have to plug points into this equation, and then you can find your infinitely many solutions. So systems which intersect along a line are called dependent. They're consistent because they do have a solution, and then they're dependent because they have infinitely many solutions. So what we're looking for when this happens is as we solve the system, we're looking for the variables to disappear. And you're looking for some sort of true equation to happen. So for example, in section 8.1, we would end up with the equation maybe like 0 equals 0. Or we could end up with like 5 equals 5 or something like that, something that's true. That tells you that you're dealing with equations where they're replicas of each other, they're laying on top of each other. And then if that is the case, then you know that your solution is not going to be specific. Since it's infinitely many points, you're looking for a formula for how you could find those points. Okay, so we're going to do 2 of these examples because in my opinion, for this whole chapter that we're doing, this is probably the most difficult thing we're about to do. And it's not terrible, it just is a little weird. So let's look at this problem. When I looked at this one, you could, again, kind of eliminate any variable. I didn't want to eliminate z because I did that last time, so I looked at the x's. And the first thing I noticed was that 2 and 10 could eliminate if I multiplied the first equation by 5. So that's what I decided to do. I decided to do the first and the third, and I multiplied the first equation by 5. So 10x plus 5y minus 5z equals 5. And then I'll just copy the third equation down. So the x's disappear. We have negative 9y plus 3z equals 15. So now I'm going to hang on to that one. And then from here, I have to use the second equation. I can use the second with the third or the second with the first. And the second with the first is going to be a little bit easier to eliminate the same variable, the x. And so I'm going to take these and I'm going to make them both 6 so that they can eliminate. So I'm not going to multiply by 5. I'm going to multiply by 3 on the first line, and I'm going to multiply by 2 on the second line. So if I multiply by 3, I get 6x plus 3y minus 3z equals 3. And when I multiply by 2, I get negative 6x minus 6y plus 4z equals 2. Those cancel. Negative 3y plus z equals 5. And so I have 2 equations and 2 variables. I'm just going to write these together. And my goal is to, again, cancel out another variable. I have 2 equations and 2 variables, so I need to get rid of another variable. So I'm going to look at the z's. This is a positive 3, so I want this one to be a negative 3. So that's 9y minus 3z equals negative 15. And I'll copy down the second equation. And you might already be noticing what's about to happen. Cancel out, so we get 0. Cancel out, we get 0. So what just happened is we were trying to solve our system of 2 equations, and we ended up with no variables and a true statement, 0 equals 0. So this is where we know that we have infinitely many solutions, and now we just have to write a formula for how those solutions can happen. So if we were doing a problem in section 8.1, we would say, well, the answer is the ordered pair xy, and to find a solution, or in this case, I guess it'd be yz, and to find a solution, just use one of these equations, and that would help you find the solution, and we'd be done. Now the problem here is that we have 3 variables. We have an x, we have a y, and we have a z. And so we have to have a formula that's going to help us find all 3 of those variables. So I need to be able to find x and y and z, all 3 of them. So what I'm going to do is I'm going to take one of these 2 equations. I'm going to do the first one because it's a little bit more simple. And it doesn't matter which variable, but I'm going to isolate one of them. So z would be the easiest to isolate, so I'm going to get that one alone, and I'm going to add the 3y to the other side. So the formula to find your z is to calculate 3y plus 5. And that tells me that when I find a formula for the x, a formula for the y, and a formula for the z, they're all going to be in terms of y. And this is kind of arbitrary. There are actually 3 different answers to this question. There's one answer that has all of them in terms of x, one answer that has them all in terms of y, and one answer that has them all in terms of z. And everybody could get different answers depending on which variable they eliminated in their first step. So we're going to do ours in terms of y. So I have 3y plus 5, and the y is just going to be y, because that's the variable I'm using. And so now I need to find the formula for how we could solve for x. And to do that, I'm going to take the y and the z that I've already solved for, and I'm going to go back to the original equations and plug them into one of the original equations. And the first one looks the most simple, and so that's what I'm going to use. So 2x plus y minus z, which is 3y plus 5, equals 1. Okay, and my goal is to solve for x, and the x should be written in terms of all the y's. So 2x plus y minus 3y minus 5 equals 1. 2x minus 2y minus 5 equals 1. So I'm going to get the x alone on the left side by just moving everything else to the right. 2x equals 2y plus 6. And then I can divide everything by 2. So x is y plus 3. So here is our formula for getting the ordered triple. We're going to have the x coordinate's going to be y plus 3, the y coordinate is y, and the z coordinate is 3y plus 5. And this is going to be where y is any real number. So, and if you wanted to come up with an example of a solution, you could. You could say, like, for instance, we could say that y is 2, maybe. And then if y is 2, then y plus 3 would be 5. Then the x-coordinate would be 5. And the z-coordinate would be 3 times 2 is 6 plus 5 is 11. And the z-coordinate would be 11. Now, your textbook, when they did this problem, they eliminated a different variable first than I did when I did this problem. And I wrote it on my notes. They ended up with this solution right here. So I just want to show you that you can have multiple answers. This is what your book ended up with. X for the first coordinate, x minus 3 for the second coordinate, 3x minus 4 for the third coordinate. And if you look at this specific point, it still works even if your answers are in terms of x. So 5 minus 3 is 2, 3 times 5 is 15, minus 4 is 11. So you'd get the same, the answers look pretty different, but they're just formulas that are eventually going to give you the same points. And of course, there's a third formula that's in terms of z, and that would have been the right solution as well. Okay, so I know that's kind of, we got in some weird territory there with that problem, so we're going to try another one. All right, and your paper will just have this printed, but I decided to use a different problem. Okay, so we're going to start off by choosing 2 equations to work with. For this problem, right away I can see that the y's are going to be kind of nice to work with, so I'm going to do equation 2 and 3 to just get rid of the y's to begin with. So I've got negative 3x plus 5y plus z equals 16, negative x minus 5y plus 3z equals negative 20. So negative 4x plus 4z equals negative 4. And then now I have to use the first equation, and I'm going to use the first equation and the third equation so that I can get rid of the y's again. So I've got negative 5x plus 5y plus 3z equals 14. And then negative x minus 5y plus 3z equals negative 20. So negative 6x, positive 6z, negative 6. So at this point, I have two equations with two variables. And the x's and the z's look like they're going to be equally easy or difficult to eliminate. So I'm just going to look at the x's. I'm going to make them both 12. So I'll take this one and multiply it by 3 to make it negative 12. I'll take this one and multiply it by negative 2 to make it positive 12. So negative 12x plus 12z equals negative 12. 12x minus 12z equals positive 12. So we get 0 equals 0, which is what we expected to happen because we're doing another example of the exact same thing. So whenever this happens, you end up with a true statement. Your variables have disappeared and you have a true statement. That means that you have infinitely many solutions. And so you need to go back to one of these equations and isolate one of those variables. So I've got x and y and z. And I'll go with this one. So negative 4x plus 4z equals negative 4. And I'll go ahead and get the z alone again. I'm going to add the 4x over to the other side. So 4z equals 4x minus 4. And then I'll divide by 4. So z is x minus 1. Z is x minus 1. That means the x is just x. So we have to find y, and we're going to do that by going back to one of the original equations to plug this in, and it doesn't matter which equation we do. So I'm going to go ahead and use this bottom equation right here. They're all kind of have equally big numbers, really. So negative x minus 5y plus 3 times z equals negative 20. And my goal is to get my y alone. So I'm going to subtract the 2x to the other side and add 3. So negative 5y is negative 2x and negative 17. So we're going to have fractions on this one. And I'll be honest, when I was doing this by myself, I didn't feel very confident in my answer because of all these fractions. And so let me write this up here. 2/5 x plus 17/5. So what I did is, because I didn't feel confident in the first answer, I went back and I said, well, I took the third equation. Let me try one of the other equations. So I went back and I tried the first equation and I plugged in x and I plugged in z. And when I plugged in x and plugged in z in the first equation, I still got the same thing for y. So that means I did it correctly. It just happens to not be a very nice answer. So this is how you get your x, your y, and your z coordinate for this particular problem. So your solution would be x, comma, 2/5 x plus 17/5, and then x minus 1. And that is where x is any real number. All right. There are several ways that three planes can be positioned so that there is no point that lies on all three of the planes. If there are no points in common to all three planes, the system is inconsistent, meaning it doesn't have a solution. And then you don't think about dependent versus independent because it has to have a solution to think of one of those two options. So here's one example where you could have three planes crossing but not have a solution. There's a lot of different ways that you could imagine this happening, where essentially like three sheets of paper could cross and not cross at a single point. So even though our most common type of problem that we're going to solve is where three planes cross and you get 1 point as the answer, it's probably not in reality the most common situation that would happen. It's probably more common that you would have no solution, to be honest. But these problems are not very interesting and they're pretty easy, and so we don't end up doing a ton of these. So this is going to be called the inconsistent system. Remember, inconsistent systems do not have solutions. So we're going to look at this problem and just see what happens, what it ends up looking like. So just like in the other problems, I'm going to try to eliminate a variable, and right away I notice that the z's look ready to eliminate, and so that's where I'm going to start. So I have x plus 2y minus 3z equals 9, and x minus y plus 3z equals 3. So 2x plus y equals 12. So now I have to use the first equation, and I'm going to go ahead and use the first equation and the third equation because this is negative and this is positive. Positive 3, so I'm going to need a negative 3 here. So I'm going to multiply this one by 3. So I have 3x plus 3y minus 3z equals 15. And then this equation down here, x minus y plus 3z equals 3. 4x plus 2y equals 18. So I'll bring my two equations together, two equations and two variables. And I can see that the x's can cancel out. This is positive 4, so I want this one to be negative 4. So I'm going to multiply by negative 2. And what ends up happening, these cancel, is that we end up with an equation that is not true. So just like in section 8.1, we have variables that disappear. But we end up with a false equation. Like in this case, 0 equals a number negative 6. And so once this happens, we would say the answer is no solution. All right, so now what we're going to do is we're going to use this process to solve some problems that are not just systems of equations, but can be solved using the process of systems of equations. So here we have a parabola in standard form, y equals a, x squared plus bx plus c, and we're going to have to find the values of these coefficients and the constant to be able to write the equation of the parabola. So generally speaking, if you have 3 unknown values, a, b, and c, then you would need 3 equations to be able to find those 3 unknown values. So here they gave us points, and each of these points is an xy coordinate. So we're going to plug them in for x and y in the equation, and they're going to leave a, b, and c as variables to solve for. So for the first equation, we've got y equals a times x squared plus b times x plus c. For the second equation, we have y equals a times x squared plus b times x plus c. And for the third equation, we have y equals a times x squared plus b times x plus c. So our three equations that we're working with are a plus, not plus, b times -1 would be minus b plus c equals 10. A plus b plus c equals 4. And 4a plus 2b plus c equals 7. All right, so the first variable that I'm going to eliminate is, I just see all the c's are alone, so I'm going to eliminate the c's first. So I'll go with the first two equations, and I need them to be opposite signs, so I'm just going to take this one and multiply by a negative. So I have a minus b plus c equals 10, and negative a minus b minus c equals -4. And I'm going to luck out here because the a's are going to eliminate and the c's, and I get -2b equals 6. And so b is -3. So that was kind of a unique situation. Now I have to use the third equation, and I'm going to go ahead and use the third equation and the negative version of the second equation that I already found. So negative a minus b minus c is -4. 4a plus 2b plus c equals 7. Equals 3. I know that b is -3 because I just solved for it. Okay, so this problem is already working out a little bit differently from the other problems we've worked with before, just because we randomly happened to solve for a variable in the first step, and that's not very typical. So I was able to find b from eliminating my first variable, and then when I worked with the next two equations, that allowed me to find the second variable. So now I just need to take the two variables and go back to one of the original equations, it doesn't matter which one, plug them both in. So I'm going to use a plus b plus c is 4. 2 plus -3 plus c is 4. And so c is 5. And this time I'm not going to write my answer as an ordered triple because this is not about lines crossing. This is about writing the equation of a parabola. So I'm going to have the parabola y equals ax squared plus bx plus c. And if you wanted to check your answer, you could graph this and then make sure that these 3 points were on the graph. All right, now at this point, you probably are feeling pretty good about these problems or have a pretty good sense of how they're working. So if you feel like you don't need another example, that's totally fine. I would stick around for the setup of this problem. And then if you want to work it out on your own, and then fast forward to the solution at the end, you can, or if you just want to leave it, that's fine too. This problem is a little bit of a bear. And what I mean by that is it's the answers are not very nice. They're all decimals. But we're going to go through it anyway. And then if you want to just kind of see how to work through a problem that gets a little bit convoluted, then this could be a good one. So it says Lionel delivers milk, bread, and eggs to Marcy's camp store. On Monday, the bill for 8 half-gallons of milk, 4 loaves of bread, and 6 dozen eggs was $42.86. On Tuesday, the bill for 5 half-gallons of milk, 10 loaves of bread, and 3 dozen eggs was $47.57. On Wednesday, the bill for 2 half-gallons of milk, 5 loaves of bread, and 7 dozen eggs was $34.72. How much is Thursday's bill for 1 half-gallon of milk, 2 loaves of bread, and 1 dozen eggs? So normally, the clue that I would use to define my variables, x, y, and z, in this case, because we have 3 unknowns, is I would look at how the question is phrased. And in this case, the question isn't phrased in a helpful way because they are asking about Thursday's order. So if we look at the context, we can see that we're talking about milk, bread, and eggs, but we're specifically talking about how much things cost. So X is going to be the cost of a half-gallon of milk. Oops. Y is going to be the cost of a loaf of bread. And Z is going to be the cost of a dozen eggs. And then each of our equations are going to be the order for Monday, Tuesday, and Wednesday. So Monday was 8 half-gallons, 4 loaves, 3 dozen eggs for $42.86. Tuesday was 5 half-gallons, 10 loaves of bread, 3 dozen eggs. Sorry, this was 6 dozen. 4 loaves of bread and 6 dozen eggs. Okay, this one was 3 dozen eggs for $47.57. Wednesday was 2 half-gallons, 5 loaves of bread, 7 dozen eggs for $34.72. And what they want you to solve, or in this case, what they want you to solve and then plug it back in, is Thursday's bill, which is 1 half-gallon, 2 loaves of bread, and 1 dozen eggs. So we're going to figure out the cost of this at the end. All right, so when I looked at my variables to eliminate first, I noticed that my y's could all kind of go into 20. And so I decided to work with my first 2 equations first. And I thought that I would multiply my first equation by -5 to make this a -20y, and that I would multiply my second equation by 2 to make that a +20y. So I got -40x minus 20y minus 30z is -214.30. I didn't just do that in my head, I did it ahead of time. And then 10x plus 20y plus 6z equals 95.14. And when I added those up, I got -30x, the y's canceled, -24z, and -119.16. Okay. And then I also, when I was working with the third equation, I went ahead and did the third equation and the second equation. And I took the second equation, and I actually didn't do 20 this time. I just did 10y and -10y. So I kept this as 5x plus 10y plus 3z is 47.57. And then this bottom equation I multiplied by a -2 to make this a -10y. So -4x minus 10y minus 14z equals -$69.44. And that gave me x, the y's canceled, -11z and negative 2187. So I have two equations and two variables. And when I looked at this, I thought, the x's look the most easy to eliminate. And so I took the bottom equation and multiplied it by 30. So I'll copy the first equation down. And the second equation is 30x minus 330z equals negative 65610. And this is around the time I really started to not feel very confident about my answers, but I kept going. And so I ended up getting negative 354z equals negative 775.26. And I divided by the negative 354, and I got z is $2.19. So the cost of a dozen eggs was $2.19. And I was like, well, I don't know, that kind of makes sense. So we have our two equations that we were working with. We have this equation right here and this equation right here. And I thought, that this one is definitely the one I want to solve for x in. So x minus 11 times $2.19 and 11 times $2.19 is $24.09. And so if I add the 2409 to the other side, I get that x is 222. And so that's a half gallon of milk is 222, which is, that's okay. That's maybe not reasonable for current prices, but that I could see that being a reasonable answer at some point. So at this stage, I needed to go back to my original equations and choose one of them to plug x into and z into. And when I looked at this, none of the equations look great, but I decided to use the third one. So 2 times x plus 5y plus 7 times z is 3472. And so if you add 2 times 222 and 7 times 219, you get $19.77. And so I'll subtract that over. So 5y is $14.95. That means that y is $2.99. So $2.99 for a loaf of bread, like, meh, okay. So at this point we have our three prices. These are not my answers, these are just our three prices. And I wanted to feel better about my answers at this point, so what I did here is I took my three answers, 222, and I stored this as z. Nope, stored that as x. 222 is x. There we go. 219 store as z. 299 store as y. So I have x, y, and z all stored in here. And then what you can do is you can type in your equations. 8x plus 4y plus 6z should equal 4286. It does. 5x plus 10y plus 3z should equal 4757. It does. So that helped me to feel better about my answers. So once we're done with that, then we can go ahead and take those numbers and find the final answer. Thursday's bill for 1/2 gallon of milk, 2 loaves of bread, and 1 dozen eggs. That's 1x plus 2y plus 1z. 1039. So 1x plus 2y plus 1z is 1039. So Thursday's bill is $10.39.